Hello everyone, my name is Nikolas Goodrich and I'm a data science developer specializing in Python for the defense and intelligence sector.
Hi, I'm Kevin Bodkin. I work as a staff scientist in a computational neuroscience lab at Northwestern University.
And we'd like to thank you for joining us today for our Capstone presentation on multi-agent reinforcement learning, or MARL for short.
So to sum it up, our problem statement is, how do we maximize group reward in a cooperative task where individual agents have limited knowledge about each other? Before we get into MARL, here's a quick recap of reinforcement learning. Reinforcement learning refers to a learning agent interacting with an environment and learning from its experiences. Unlike supervised or unsupervised learning, the agent is not provided with a data set. Instead, it produces its own data by interacting with the environment. In this situation that we see at the right, the agent performs some sort of action, sees how it affects the environment, observes the state from that, and then will perform an action. And dependent on whether that is a beneficial or not beneficial result, it will decide whether to perform that action more frequently in the future or less frequently.
Our experiment used the water world environment from Stanford Intelligence Systems Laboratory. It's like an underwater Pac-Man where agents such as fish consume food, here in green, and avoid poison, the smaller ones. We tested collaborative and competitive interactions, varying food distribution and adding obstructions. Both multi-agent and single-agent examples were trained using proximal policy optimization, a policy gradient method that balances training complexity, sample efficiency, and stability in reinforcement learning. And to enforce the agents to collaborate, two agents must touch one piece of food at the same time to receive a reward. We also have the curse of dimensionality. As the volume of sample space grows, the data becomes incredibly sparse. Functionally, we're making decisions based on less information. In Marl, the dimensions of the problem explode as we incorporate more agents. It gets complex quickly as the data grows, which can overwhelm our learning algorithms. If there are fewer variables, the results are more conclusive.
Joint training has been shown to help reduce some of these issues. We are working to extend a joint policy method from Gupta et al. In their paper, they were working with trust region policy optimization as their underlying learning mechanism, which is a particular style of gradient policy optimization. We are adapting this to work with OpenAI's more computationally efficient proximal policy optimization.
Our experiment used the water world environment from Stanford Intelligence Systems Laboratory. It's like an underwater Pac-Man where agents such as fish consume food in green and avoid poison in salmon color. We tested collaborative and competitive interactions, varying food distribution and adding obstructions. Both multi-agent and single-agent examples were trained using proximal policy optimization, a policy gradient method that balances training complexity, sample efficiency, and stability in reinforcement learning.
As a baseline comparison for all of our future analyses for multi-agent stuff, we trained a single agent to work independently in the environment. We trained the agent in blocks of 10,000 steps, then evaluated the agent 10 times on the environment, initialized with 10 different seeds. The plot that we see here is the average of the number of rewards and the standard deviation for each of those 10 training environments over the course of the training. As we can see, as the agent continues to learn, or as it's trained over time, the number of rewards improve. The interesting thing about reinforcement learning is that it's not necessarily always monotonic, meaning it doesn't always straight increase or decrease. Here's an example video of what the best version of the single agent interacting with the environment looks like. As you can see, it's bouncing around, attempting to find those green pieces of food while avoiding the poison. It does an all right job.
When introducing multiple agents, the strategy changes drastically. In this current setting, no communication protocols have been established. The agents do not see each other as anything other than random objects in the environment. One potential reason that they're grouping in the corner is a need for more exploration. The agents must balance between using the policy and experimenting. We altered the entropy to allow more time to explore, which could cause the agents to stop grouping. There is no communication, and therefore no collaboration.
And here we see the mean performance, as we showed before with the single agent, for these four agents. And over time, as they're training, their performance actually continues to get worse. This is something that can happen if you end up in a situation where it can't find a policy that works in any sort of real way, and it just fixates on one and continues to move forward. However, what we see is as soon as we introduce some level of communication, in this case in the form of parameter sharing during training, the training actually improves over time, and the performance improves as well. We did end up running this, as Nick had mentioned multiple times, there is the issue with dimensionality, so the training just takes a lot longer. So if we take that same model with some parameter sharing and allow it to run for a much longer time, in this case 4 million timing steps, we do find that it starts to improve quite a bit. Here we see three different visual examples along the training process of the multi-agent environment. On the first one, on the left, what we see is they have learned that they need to touch food together, but they haven't learned any sort of way to work together. So as a result, they all cluster in the corner, and when a food ends up getting close enough, they might reach out and grab it, but then they just stay in the corner and waste all their time. In the middle one, they've started to learn to explore a little bit. They bounce around some, and they're able to do single agent things fairly well, so they avoided poison all right. But they have a hard time staying together enough that they can actually get the food. On the third one, what we see is that they're actually able to cluster together and do some sort of exploration while staying close enough that they can get a reward.
In summary, we have shown a few multi-agent systems attempting to cooperatively receive rewards in the SISL Waterworld task. So far, we have found that training the agents independently on the cooperative task results in agents that are unable to learn a successful task. We were able to improve this somewhat by training agents with shared information in a much longer training period. We are still in the process of improving our parameter sharing and hope that it will improve our cooperative training. So moving forward, my plans personally are to take this knowledge of reinforcement learning and multi-agent reinforcement learning and apply it to my career, because I work in the defense industry where a lot of data sets just don't exist. We work in a very unique market, and by applying this knowledge, I hope to be able to generate more data sets for us to use in the future.
As I mentioned previously, I work in research neuroscience, and I've actually been thinking about ways that I could apply this to, behavioral paradigms or other similar paradigms. And I've been thinking a little bit about treating this as a distributed nervous system, right? Where you could have something like an octopus that has ganglion or clusters of nerve cells at different control locations within the body, and then some sort of central supervisor that works to communicate between them. And I think that could be an interesting way to take MARL in the future. If you want to learn more about MARL, we recommend a very brief paper, a very condensed survey, that's the name, a very condensed survey of MARL by Hernandez, Leak, Cartal, and Taylor. And this provides a very information-dense, page-long overview. For a more in-depth overview, there's several options that are very good, but we particularly recommend Gronauer and Diepold's 2021 review. For a thorough lesson on single agent learning, we recommend Reinforcement Learning and Introduction, second edition by Richard Sutton and Andrew Bartow. This is viewed as like the gold standard of learning reinforcement learning. And they, nicely enough, actually offer a PDF copy that they keep updated online. So just Google it and you'll find it. Additionally, University College London and Google's DeepMind put out a series of fantastic free videos covering everything in modern reinforcement learning, from basic tabular learning all the way to deep policy gradient methods.
Thank you so much for watching our presentation today. Feel free to reach out to either one of us if you have any further questions.